Hi guys, and welcome to this session on elastic potential energy. This is mentioned in P1, it's also in energy, and it's also mentioned in P5, forces of motion. So this is what we're going to go over today. We're going to look at what elastic potential energy is. We're going to use the elastic potential energy equation, and we're going to combine elastic potential energy with other forms of energy. So, what is elastic potential energy? Well, if you have an object like a spring, for example, what you can do is if you apply a force to it, you can either compress it, and you need two forces to do that. You can extend it, and by doing this, you need a force. And when you're doing that, you are storing elastic potential energy. So, elastic potential energy is the energy stored in a body because you are changing its shape. This doesn't have to be a spring, it could be other objects as well. Springs are the most common example to bring this up in. Now, how much energy you store in it depends on two things. So one, it depends on how much you extend it, or how much you compress it, or you increase its length. So if you like, the change in length is the one of the factors. Another thing is something called the spring constant. So if you think of a spring constant is given by the symbol K. Spring constant is the amount of force required to extend a spring by a certain amount. So let's say, for example, it's measured in newtons per meter. If you had a spring constant of 10 newtons per meter, that means for every meter of extension, it requires 10 newtons. So those are the two things that it depends on. Now, different things have different spring constants. So if you look at something like on the left, you've got a mattress spring. They have quite a high spring constant. That's because you want quite a lot of force to extend it by a certain amount. Because if you sat on a bed, or if you lay on a bed, you don't want it just to compress straight away. You want it so that you need a lot of weight, a lot of force to compress it. Otherwise, it would just go flat. And then you've got something like a spring from a pen that has quite a low spring constant, so you need a little force to extend it by a certain amount. So that is what elastic potential energy is. Energy is stored in the body depending on how much you change its length. So looking at the equation, you get given the equation. This here, E little e with the subscript E, that means elastic potential energy, because you can have different types of energy. So for example, you can have kinetic energy, which would be E with a little k like that. So elastic potential energy is equal to half, so just 0.5, times this spring constant, times by the extension, and you have to square the extension. So you've got to look at the units. So spring constant is normally newtons per meter, and therefore the extension needs to be in meters. But if you get given the spring constant in newtons per centimeter, you can have the extension in centimeters. As long as this bit and this bit are corresponding, that is absolutely fine. This equation is given to you, so you don't need to remember it. A few people do have a few issues using it in some questions. Now, this equation only applies provided the limit of proportionality is not exceeded. So if you imagine you have a graph where you have force against extension. So to start off with, you should get a nice straight line where the force is directly proportional to extension. If you double the force, you double the extension, straight line through 0, 0. But if you carry on adding a force, what can happen is the graph can change and the graph will start to curve because the force is no longer proportional to the extension. So in this region here, where you get a straight line, this equation and the other one, which is one for Hooke's law, those both apply. But as soon as you exceed this limit of proportionality, i.e. your graph starts to curve, then this equation falls apart. So here's an example. If you want to have a quick go, pause the video and then look back at it. Okay, so here are the answers. One of these is correct. It is that one. So here's some more. If you'd like to have a go at them, press pause and then I'll show the answers. Right, okay, here are the answers. One I wanted to go through was this final one here, the challenge plus. I just want to show you how to do it. So whenever you do an equation, the best thing to do, first off, just write the equation down. So you've got E equals half times K times E squared. Then what we need to do is we need to fill in the gaps. So the energy is 16, so that goes there. Half is just a half. We want to work out the spring constant, so let's leave K there. And look, the extension is 16 centimeters. You get 1 mark straight away. You change centimeters into meters. So to do that, you'd have to divide it by 100 because there are 100 centimeters in a meter. So that should be 0.16. So if we now put 0.16 in there, with these questions with the equation, you won't get any marks for just stating the equation because you're given that. But you'll get marks for changing in the units you need to, and sometimes you can get marks just to literally plug in the numbers in the equation like I've done there. That was easy. I just got the equation, put the numbers in the right place. Really, really straightforward. Some people get carried away on what to do next. I said the next thing to do is simplify it. So 16 equals 0.16 squared. So if you do that in the calculator, and then we might as well half it because it's on the same line. And you get k times 0.0128. Just a bit of simple algebra here. We've got to divide both sides by 0.0128 divided by 0.0128. That will then cancel out this. And there's your answer. 16 divided by that is 1,250 newtons per meter. Okay, so combining it with other forms of energy. So if you look at energy transfer, energy is conserved. It cannot be created or destroyed. It's always transferred from one form to another. So if we give this example, a spring in a gun has a spring constant of 10 newtons per meter. If it's extended by 0.2 meters, how fast will a 100-gram bullet leave the gun? So let's talk about the energy transfer to start off with. Here in the top one, we've given that spring elastic potential energy because we've extended the spring from its original length. Now, what's going to happen is as soon as you release that spring, the elastic potential energy is going to be converted into kinetic energy. Now, in these questions, we assume that things like friction don't really apply, therefore that this energy is not transferred into heat. It's purely transferred into kinetic energy. So we need to work outside with how much elastic potential energy is actually stored in this spring. So let's use the equation that we've been given already. So we've got elastic potential energy is equal to half times k times extension squared. We know if the extension is 0.2, we know that half is a half. We don't know the elastic potential energy, we know the spring constant is 10. So if we work that out, we've literally just going to have 0.5 times 10 times 0.2 squared, which is equal to 0.2. So 0.2 joules worth of elastic potential energy. Right, so that's how much elastic potential energy you have, but if you have that to start off with, that must all be transferred into kinetic energy. So if we remember the kinetic energy equation, which you do need to learn, kinetic energy is equal to half times mass times speed squared. So we then need to substitute some numbers in. We know half's a half. We know the energy is 0.2. We had that much elastic potential energy beforehand, so we're going to have that much kinetic energy afterwards. The mass, it says it's 100 grams. Mass is the only thing that has a prefix in front of it, i.e. mass is the only thing with something like kilo in front of it. So we need to change 100 grams into kilograms. So there are 1,000 grams in a kilogram, so we divide 100 by 1,000, you get 0.1. Again, do that to start off with, and that is a mark straight away. Right, we don't know what speed is, so times speed squared. So simplify it to start off with. We do 0.2 equals half times 0.1, which is 0.05. We divide both sides by 0.05. That's that stage. Divide both sides by 0.05, and that side then simplifies to v squared. 0.2 divided by your answer gives you 4. So now we're on 4 equals v squared, and then to do that, square root of v squared is just v. Square root of 4 is 2, so v equals 2 meters per second. There we go. Right, so just a reminder, these equations are not given to you. Kinetic energy, half times mass times speed squared. The other equation they could use as well is gravitational potential energy. So this is energy by the position you are in a gravitational field, m being the mass, g being the gravitational field strength, and h being the height. You could have this question where, I don't know, you have the gun firing upwards, and you've got to work out the maximum height. So I'll tell you what, let's have a quick go at that. So if we've got this, and let's say we want to work out the maximum height, same thing. To start off with, that gun is going to have elastic potential energy, and it's going to be converted to gravitational. We said to start off with that the elastic potential energy was 0.2. So we could say 0.2 is equal to m times g times h. 0.2 equals, we know that's 0.1. G is 9.8 on Earth, and then we don't know what h is. So if we simplify this and we do 0.1 times 9.8, we get 0.98. And then we do 0.2 divided by 0.98, we should get 0.204, which will probably just be rounded to 0.2 again. So we go 20 centimeters in the air. Okay. If you want to have a practice, here are some questions. Pause the video and I'll reveal the answers. Okay, here are the answers. There you go. Cool. Hope you enjoy, guys. See you next time.